Yes, hello and good morning. Today we're going to start talking about Chapter 4 today, entitled Probability. As you may recall, we talked about three major subtopics in the course. The first was descriptive statistics, where we learn how to organize, visualize, and find ways to interpret raw data. We're going to call that portion of the course done. On we go then to probability, the second major portion of the course. And you may recall in probability, well, in wide strokes, what we do is seek ways to measure chance. And I'll just put down here as a rough definition. It's defining a numerical measure of chance or likelihood of events happening. We'll be able to actually tack numbers onto the likelihood of an event happening or not. And let's keep an eye on where we're going. Eventually, we want to go to inferential statistics, and where we make inferences about populations based on data from samples. All right, so probability is the topic of the day here, opening up Chapter 4, and we're going to start with Section 4.2, Chapter 4, Section 2, which is entitled Basic Concepts of Probability. All right, let's talk about almost the simplest possible example. Let's roll what we call a fair die. That means a die that has numbered sides 1 to 6, and each side is equally likely to come up in a toss. And if I ask you, what's the probability of rolling a 5? Well, of course, you'll tell me there's 6 possible outcomes, and only one of those is a 5. So the probability of a 5, or the probability of any number on a fair die, is 1 to 6. Of course, that may be a bit simple. In general, we label events as capital letters, or just describe the event in words. If I ask for the probability of A, well, I'll define the probability. I'll read this just like function notation. It's the probability of event A, or I'll just simply say the probability of A. It's defined as the number of ways event A can occur divided by the total number of possible outcomes in the experiment. In the above example, well, we can easily see that there are 6 possible outcomes in rolling a die, and only one of those outcomes corresponds to a roll of 5. Hence, we get the probability 1/6. Alright, this is what the book calls the classical definition of probability. I want to look at example 2 on page 137. They refer to smokers. Let's say they take a survey of 1,010 people, 1,010 adults, and that reveals 202 of those 1,010 people are smokers. So if I cite this experiment, I'll say if one adult is randomly selected from that pool of 1,010, find the probability of getting a smoker. I'll write this out a little more formally. Find the probability of choosing a smoker from that pool. Well, I'll say the probability of finding one smoker, and I'll abbreviate that event in words like so. The probability of finding one smoker in this experiment, well, of course, you're going to say there's 1,010 ways to pick a person from this pool, and there's 202 ways to find a smoker. And if I grind this out, I get a 0.200, the textbook states, as a probability. Okay, so again, another very simple example of measuring likelihood or chance in a probability experiment. All right, this one's not out of the book, so I guess it's kind of included in a homework problem in another way. Let's write this out here. Example, I'm going to say a couple. Let's suppose a couple has 2 children. Right, I'm not going to ask you for probability yet. I'm going to say list all possible outcomes. Let me erase that. List all possible outcomes gender-wise in this experiment, allowing any child to be of any gender in any order. Well, when you're having children, there's 2 possibilities for each child. And what I can do is say, well, there's 2 possibilities for the first child, gender-wise, times 2 possibilities in the second child, gender-wise, and that comes out to 4 possible outcomes. And I'm going to summarize these with what we call a tree diagram. Hopefully you've seen these before somewhere in your math career. If I allow for the first child to be a boy or a girl, each of these outcomes tails off to 2 other outcomes, also possible to be a boy or a girl, and all possible paths from left to right each possible path from left to right is a possible outcome for this experiment. All right, so my list of possible outcomes, gender-wise, allowing any child to be of any gender in any order, is going to go like this: boy, 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 girl, girl, boy, girl, girl. We're of course reading left to right. The first letter is the gender of the first child, and the second letter is the gender of the second child. I call this list a sample space. Now that's a fancy name which really describes all possible outcomes of the experiment. So the sample space is really a list of all possible outcomes of the experiment of interest. Okay, so sample space, fancy name for the list of all possible outcomes. Alright, so if we're having 2 children and all possible outcomes can be expressed in that list of 4 outcomes. Alright, so let's remember that if you have 2 children, you've got 4 possible outcomes, again allowing any child to be of any gender and in any order. Another example, let's assume, again, we're still talking about having children. Let's say a boy or a girl is equally likely in any birth. And that's pretty much the accepted value. There's no real probability advantage to either of the genders in common practice. Alright, we're going to assume boy and girl are equally likely in any birth. Alright? Let's say a couple, again, has 2 children. I'll say find the probability. Let's see, hang on, let me be a little more specific about this. A couple has 2 children. Find the probability of one girl in those two children. Alright, I'm going to do this in a brute force fashion. Of course, later on in the course, we're not going to item by item list the sample space, but we can here in this experiment. Well, the sample space is boy, 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 girl, girl, boy, and girl, girl. Alright, so the probability then of one girl in this experiment is going to be what? Well, you've got 4 possible outcomes, and I claim 2 of these outcomes have one girl. I can list them here. This outcome has one girl, and this outcome has one girl. Please note that the statement one girl means exactly one girl. That means one girl and one boy by implication. Okay? So one girl, exactly one girl, equivalent to one girl and one boy. So we've got 2 of these outcomes correspond to one girl out of 4 possible outcomes. Hence, the probability of one girl is 1/2 or 0.5. Okay? Alright. Let's do something a little harder here. Get a fresh screen. And I believe this is modeled after one of the homework problems. Again, we'll assume a boy or a girl is equally likely in any birth. Let's say this time a couple has 3 children. And I'll ask this: find the probability. Find the probability of getting 2 girls in these 3 births. Somewhat similar, but a little more complicated. Well, the first thing you have to ask yourself is, what is the number of possible outcomes allowing any child to be of any gender in any order? Well, let's see. Just like in the 2 case, like in the 2-child case, well, we've got a first child and a second child and a third child. Right? They can each have one of 2 possible genders in each slot. And if I multiply these across, I get 2 times 2 times 2 equals 8 possible outcomes. Not 6, not 9, 8 possible outcomes gender-wise in 3 births, allowing any child to be of any gender and in any order. Alright, what I'm going to do is list the sample space here, and what I can do is make another tree diagram. Let's say I've got a first child, and the first child can be a boy or a girl. And each of those possibilities tail off to 2 other possibilities for the second child, and that can be a boy or a girl. And each of those possibilities tail off to 2 more possibilities for the third child. Boy, girl, boy, girl, boy, girl, and boy, girl. Now, each possible path from left to right is a possible outcome in this experiment. So what I'm going to do is list the sample space, a list of all possible outcomes: boy, 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 girl, boy, girl, boy, boy, girl, 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 boy, boy, girl, boy, girl, 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 boy, and girl, girl, girl. Right, those are 8 outcomes. I've listed the 8 possible outcomes, and I believe I've exhausted all possibilities with no duplication. Alright, so I want to ask or answer the question, what's the probability of 2 girls in 3 births? Alright, now remember, our language says 2 girls means exactly 2 girls. That means 2 girls and 1 boy. And I have to then look at my sample space and say how many of these outcomes have 2 girls and 1 boy. I believe there's one. 2 girls and 1 boy, there's one. And 2 girls and 1 boy, there's one. And I believe that's it. There's 3 of those outcomes have 2 girls and 1 boy. Alright, so I'm ready to answer my question now. There's 3 ways to get 2 girls and 1 boy, and there's 8 possible outcomes in the experiment. So the probability of 2 girls in 3 births is then 3/8, or I'll decimalize it as 0.375. There's another way I could have figured this. Well, if you're looking for the probability of 2 girls in 3 births, well, right away I know there's going to be 8 possible outcomes, as we discussed above. And if I've got 2 girls, that means 2 girls and 1 boy, and there's only 3 available slots for that 1 boy, right? There's girl, girl, boy, boy, girl, and boy, girl, girl. So only 3 outcomes out of the 8 I know will have 1 boy. 3 slots available for that 1 boy, so I can say 3 out of 8 and get the same answer a little more quickly, maybe with a little more finesse. Alright, so another expression of probability. Let's talk about the chapter problem. The chapter problem, every new chapter in our book is motivated by a statement of a chapter problem. And in this chapter problem on page 133, I'm going to turn there myself. Give me a minute. Talks about pre-employment drug screening. You may have run into this, where you apply for a job and you're forced to undergo a drug test. And if I look at table 4.1, table 4-1 on page 233 on the bottom, or page 133, sorry, at the very bottom of the page, we see a table that summarizes pre-employment drug screening results. I believe it's for 1,000 such tests. Let me summarize this table. Try again. Get this right. Alright, basically they're cross-referencing these people that underwent these drug tests, and some of these people that were tested did in fact use drugs. Some of these people did not use drugs, and we want to cross-reference them by what the machine said about them. Here there's a positive test, and by positive that means the machine said it was a drug use was indicated. Let me write that down. Drug use indicated. And the negative sign at the head of this column indicates a negative test result, and of course that means drug use not indicated. Let me write that down. Drug use not indicated. Alright, let me fill in the numbers here. We got 44, 90, 6, and 860. Alright, notice, I believe the grand sum here, 950, yes, the grand sum here is 1,000. So this represents a survey of 1,000 people that underwent a drug test for employment. Alright, from this pool, I want to randomly select one. Okay? And then I'm going to ask the question, find the probability of selecting what we'll call a false negative. Well, negative means the machine indicated no drug use, and false negative means that indeed there was drug use. So the negatives are in this column. All right? All the numbers there refer to numbers of people where drug use was not indicated by the test. All right? And if I want the probability of getting a false negative, well, let's see. False negative means there was a negative test result, but it was false. That means that the people were actually using drugs. That means there's 6 false negatives. Everybody okay with that? Negative means drug use not indicated, but 6 of these people, drug use was indeed the scenario. All right, so the probability of, let me go back to yellow here. The probability of that one person being a false negative in this story, or in this study, well, there are 1,000 people to choose from, and only 6 of them were false negative. So that means we come up with a probability of 0.006. Similarly, find the probability of a false positive. I can work this out. Similarly, the probability of a false positive, well, let's see if we, again, let me specify, we randomly select one. There's 1,000 ways to pick one person from this study. How many of those were false positive? Well, let's scroll up. False positive means that the machine said drug use was indicated, but in fact there was no drug use. So 90 people in this study were falsely identified as using drugs. That's kind of troublesome. So 90 ways to pick a false positive, over 1,000 ways to pick a person in the study, and of course that simplifies to 0.09. Alright. On we go to more definitions and notation here. Complementary events. What does it mean for an event to be complementary? Well, a picture tells 1,000 words. I'm going to draw here what they call a Venn diagram. You've almost certainly seen these in your mathematical careers. Basically, it's kind of a spatial appeal to probability type situations. If I look at this rectangle as being my sample space, essentially my universe of possibilities in any particular experiment, and I will label a circle within that rectangle as event A, and I'll keep it arbitrary, and hence we refer to everything outside the rectangle, outside the circle, but still in the rectangle, as A bar or not A. Alright, the notation A bar actually means not A, and that's how we'll read it. A bar is not A, and is defined as all possible events not included in A. Alright. We're going to use this complementary, oh yes, hang on a minute, let me scroll back. Complementary, the word complementary comes in when we notice that A bar, or not A, is the complement of A. Some books use A with a superscript of C to indicate complementary events, but we'll just use A bar. A bar is largely the notation that's evolved over the years. All right. Some notes about probability. Probability. Of an impossible event equals 0. But I am guessing that you knew that. The probability of a certain event. Well, I bet you know that's 1. Hence, all events land somewhere in between the realm of impossibility and certainty. So when we're talking about probabilities, that means the probability of any event has got to be between 0 and 1. All right. Regarding complements, if I've got some sample space defining some event A, and A bar is everything outside of A but still in the sample space, well, I think we can easily see that the probability of A plus the probability of A bar or not A must be 1. Right? Either A must occur or A must not occur, so the sum of those probabilities is always 1. In other words, the sum of probabilities of complementary events is 1. Well, that means if you know the probability of A, you can find the probability of not A just by subtracting from 1, and vice versa. If you know the probability of not A, you can find the probability of A by just subtracting it from 1. Okay? Let me get a fresh layer here. All right, an example here. Let's talk about an earn problem. Classic probability type exercise here. An earn contains, let's say, 3 red balls, 2 black balls, and 4 green balls. Again, I'm going to randomly select 1. And I'm going to ask 2 questions. Find the probability that it's green, and also find the probability that it's not green. Alright, the probability of selecting a green ball, well, you have to think, how many unique ways can you pick a ball? There's 4, 5, 6, 7, 8, 9 balls total. And of those 9 balls, 4 of them are green, so there's 4 ways to pick a green one, divided by 9 total balls. 4 over 9 reduces to 0.444 in decimal. Okay? What's then the probability of not green? Well, again, complementary events add up to 1, so the probability of the probability of not green is then 1 minus the probability of green, which would be 1 minus 0.444, and 1 minus 0.444 simplifies to 0.55. I'll call it 0.556. Of course, I could have got there a little more directly. If I said the probability of not green, well, how many balls are there? There's still 9. How many not green balls are there? Well, 5 out of the 9 balls are not green, and we get the same result, 0.555555, repeating decimal, or 0.556, I'll call it. All right, we're hitting the half-hour point, so we'll call it a day, and this concludes section 4.2, online class, basic concepts of probability.